Mantle University. Mantle seismic anisotropy, subduction-induced by three-dimensional flow.
Yeah, 너무 신기했어요. Yeah.
Okay, good afternoon. And first of all, I want to thank
Okay, that supports my
presence here at this conference. And one of the main problems in geodynamics is to reconcile seismic anisotropy observations
with the mantle flow at depth.
With the dynamics of the moving tectonic plates. And in particular, at subduction zones, up to today, there is no satisfying interpretation that can explain the seismic anisotropy observations. And so basically, the aim of this project is to make an integrated modeling of 3D subduction models that induce 3D flow in the mantle. These in turn induce mantle fabric, and from this mantle fabric we can then compute synthetic seismic anisotropy at the surface of our model. And the importance of this work, I think, is that if we are able to match the seismic anisotropy observations with our model, then as the flow in the mantle is coupled with the subducting oceanic plates, then we can really understand the full kinematic and dynamic behavior occurring at subduction zones. So mantle flow patterns are usually determined with the by measuring seismic anisotropy, and the main source of seismic anisotropy is thought to be in the mantle, in the upper mantle actually, that is deforming by dislocation creep. And when dislocation creep produces a lattice prepare orientation of anisotropic minerals such as olivine or pyroxene, and this has been measured in samples, so xenolites coming from the mantle, and also has been verified experimentally by among all Carado and Omi Yang that are present in this workshop. And as you can see here, if I deform by simple shear aggregates of olivine crystals, the first axis of the olivine orients parallel to the flow direction in simple shear. So another source, so this lattice preferentiation in the upper mantle is thought to be the primary source of anisotropy. Secondary source could be due to the shape orientation of sheeted dikes, cracks, or like fine layering of rocks with different elastic properties. And this is valid as long as the spacing between the structure is much smaller than the wavelength of the shear wave. So seismic anisotropy is usually measured with shear waves. So for example, we can use surface waves, that is the log waves that are polarized on the horizontal plane, or and Rayleigh waves that are polarized in the vertical plane. And so if I, for example, I measure the ratio of the log waves over the Rayleigh waves, I can measure what is called the radial anisotropy, and this you can see here. So this is the ratio squared. The ratio to the power of 2. And you can see that the ratio is commonly bigger than 1. That means that the log waves are faster than the vertically polarized Rayleigh wave. And also, I can also measure the azimuthal anisotropy, that is the variation of the vertically polarized wave, the Rayleigh wave as a function of the azimuth. And as you can see here, the fast Rayleigh wave is commonly oriented parallel to the plate motion, except as we will see at subduction zone where the flow is more complicated. And so these observations can be easily, I would say, interpreted as a stenospheric flow induced by the plate motion, with an anisotropy geometry where the fast axis is parallel to the flow, and then you have a slow axis that is perpendicular to is vertical, let's say, and the intermediate axis that is in the horizontal plane. So surface waves have a horizontal resolution that is quite poor. It's like
1,000 kilometers. If you want to go a bit more in detail, you have to use other shear wave phases, like for example SKS or local shear wave or source side S, and these are commonly used to study the anisotropy at subduction zones, where there is a kind of common pattern where the fast wave so basically what happens when you have these waves that travel vertically toward the surface, and if they encounter an anisotropic medium, they split into components with the fast that is polarized into the fastest, the plane with the fastest velocity. And so usually this wave is polarized parallel to the trench that is perpendicular to the plate motions. And also what is observed is that the delay, the time delay, so between the fast and slow shear waves, seems to be proportional to the velocity of retreat of the trench here. And because seismologists tend to interpret the polarization of the fast wave as the direction of mantle flow, these observations have been interpreted as a trench parallel flow below and above the slab, with a strength that is proportional to the velocity of trench retreat or advance. However, if you look at this simple plane strain deformation, where here we have compression and here is in this direction is extension, and we see that things are a bit different. So this is the vorticity number, that is the ratio between vorticity and strain rate. When vorticity is 0, we have pure shear. When the ratio between vorticity and strain rate is 1, we have simple shear. These in colors here are the streamlines, and this line here is the ISA. So this means is indicates the orientation of the maximum stretched axis of the fine strain ellipsoid that occurs for infinite deformation. And basically the Olivin fast axis orients parallel to this to the ISA. And so you can see that in simple shear you find that effectively the ISA, and so the Olivin fast axis orients parallel to the flow. But in the other cases, and especially in pure shear, the Olivin fast axis is oriented at high angles with the flow, or like is oriented parallel to the flow just locally. And so this means that the Olivin fast axis orients rarely with the flow, or just in simple shear deformation. Of course, you can argue that on the Earth, where you have convection that is bounded by the above and the bottom, simple shear deformation is the most common type of deformation. But this is not always the case, especially at subduction zones, as we will see. And also the interpretation of the seismic anisotropy is complicated by the fact that as a function of the water content, the rhetoric stress, temperature, and maybe the confining pressure, the Olivin fabric changes. And so things could be not that easy as we always thought. So a way to reduce the number of possible interpretation to explain the given set of seismic anisotropy observations is to model flow in the mantle induced by plate motions, calculate the lattice preferred orientation due to this flow in the mantle, and then also calculate the synthetic shear wave splitting. And this has been done for 2D models at the beginning, and also for 3D models. Or another way you can do, as we saw before, you can compute 3D flow models, and instead of computing the lattice preferred orientation, you just compute the orientation of the infinite strain axis, sorry. And these models produce like good results, but the thing is that they use just instantaneous mantle flow solutions. That is, they assume steady state conditions. So this means that if your system is not a steady state, this method cannot track the deformational history. And so we try to account for this deformational history in the following way. So this is the initial setup of our flow model. This is the computational domain. We use Underworld to compute 3D mechanical models. This is the oceanic plate that is subducting. We impose different width of the plate. And so the plate here has a perturbation, and then the system is left run by dynamically. We don't impose any kinematic boundary condition. And all these dots that you see here, from the surface down to 660 kilometers, each of these particles represent an aggregate of 1,000 crystals. 70% are olivine and 30% are orthopyroxene. And here at the 660s you have the lower mantle that has a higher viscosity. And the rheology of the upper mantle is non-Newtonian. So to calculate the LPO, we use DREX. There is a code, there is an open source code you can download freely from this website. And the thing is that DREX successfully reproduced the LPO derived experimentally, like in simple shear or in uniaxial compression. But there is one problem with DREX, is that it's made to just use one input velocity field. So basically, you have to assume that your system is at steady state conditions. And so what we have done, we modified this the DREX to account for forward advection of particles, 3D flow, because the original one is for 2D flow, and also we parallelize it with the OpenMP. And so this is the result for a narrow homogeneous plate. This is just a view from the mid plane, so this is half plate. And as you can see, the plate arrived at the 660, bend, and then it starts to retreat. And this axis here, so this is the transverse anisotropy. This results from the transverse anisotropy that is calculated for each crystal aggregate, and the axis indicate the symmetry axis. And because the symmetry axes are parallel to the maximum, to the longest strain axis of the finest strain ellipsoid, this axis here indicate basically the fastest direction. And so the color and the length of this axis are proportional to the amount of transverse anisotropy. And what you can see here is that below the slab you get two anisotropy domain, one that with the trench perpendicular anisotropy that is due to the entrained flow below the slab, and below this domain there is a region that goes from 200 to 400 kilometers with the trench parallel anisotropy with a strong anisotropic core here that goes up to 8-9% anisotropy. And here you can see a bit better from different views. So here you see the alignment of the fast axis that is that reproduce something similar to a toroidal flow. This view from the top, this from the bottom, where you can see this core with the trench parallel seismic anisotropy, and this is from the side. And what is interesting is that this trench parallel anisotropy is perpendicular to the flow that is trench perpendicular, and this is standard solution for 3D models of subduction and retreat of the oceanic plate. And basically you get trench parallel anisotropy because you get divergence of the flow lines, and so you get trench parallel extension, and so the olivine fast axis will align parallel to the trench. And so after this, I make vertical profiles of the elastic tensor. So each particle, for each aggregate of crystals, you can calculate the elastic tensor. Then you can make the vertical profile. And then you can use another software that is called FS Track. You can shoot shear waves, okay, long period shear waves that are SKS wave, and calculate the splitting. So this code is open source. You can download from this website. So this is from top view. This is the trench, and this is these bars here indicate the fast, the polarization of the fast shear wave, SKS wave. You can see that here you get a bit of trench parallel anisotropy, and then here a pattern that reproduces the toroidal flow, the corner flow around the slab. And this is what is usually observed at the edge of subducting oceanic plates. Like the best example is for sure on the south of Cascadia, where you get this pattern of the fast SKS waves. And these, so if we are able to match these observation with this model, and then looking at these previous the flow solutions, then we can say, okay, the flow around the slab has this kind of geometry that is quite easy to imagine also. And here I want to compare the results of the LPO and SKS splitting computed with the original advection scheme of DREX and with the new advection scheme. So basically, with the old scheme, what you do, you start from the original position of the aggregates, and you go backward in time to look for an amount of deformation that you pose at the beginning. And so basically, all your particles that you put in your domain will have a high, strong fabric, basically. While with the new advection scheme, where the particles are affected forward in time, and you change your input velocity field for each time step, you see that the only particles close to the subduction zone have a high, strong fabric. And also the other difference that below the slab with the old method, you cannot reproduce any particular pattern differently from these other models. And when you go to compute to the SKS splitting, basically you see that with the anisotropy computed with the old model has no clear pattern, while and this is the one we saw before, where you can see a clear pattern that is ascribable to the toroidal flow. And I think I ran out of time. Okay, and so I'll stop here.
Okay, thanks. There are questions, so it's time for there's a question from there. The next speaker can prepare.
That was really interesting talk. That was great. I agree with your criticism. Yeah, that was really interesting talk. I agree with your criticism about the assumptions made in the instantaneous flow models. One of the reasons it actually works for Alaska is the plate reconstructions indicate that plate boundary has been stable for like over 20 million years with the plateau. Yep. So for our models of Alaska, like we do make that assumption when we calculate the
in that case, it's fine.
So it works there, but I definitely agree. In a lot of places, you really do need the time-dependent models.
If your system is a steady state, then all these models are valid.
Yeah. So because of the history for Alaska, it works. You know. So but that's a good point.
And there was another question there. Huh?
On you.
Nobody?
No.
There. Yeah.
Have you looked at varying the width of your plate?
Yes, I didn't have time to show you. But basically what happened, if I increase the width, it becomes trench perpendicular. You see? This is like 1,000 half width. And this is because you increase colloidal motions, and the thickness of this layer with trench perpendicular anisotropy increases, and basically you get trench perpendicular anisotropy. Yeah.
Well, let me. Okay, thank you for the interesting talk. For your case, maybe the physical mechanism to cause trench parallel flow is toroidal flow at the tip of the slab.
Well, I don't observe any trench parallel flow. Let's get trench parallel anisotropy. I mean, that models with the narrow plate. Basically, what you see. No, but you say trench parallel flow. You get. A bit too far away. So here, you get trench parallel anisotropy, but the flow here is trench perpendicular. So basically, a flow that goes from there all around the slab and comes here. You get this trench parallel anisotropy because you get trench parallel maximum stretching. It's pure shear deformation. It's pure shear deformation.
So you're proposing maybe totally different mechanism from the trench rollback causing trench parallel flow. Right?
Yes. Yes.
Thank you.
Yeah, just real quick, you mentioned the ISA, the infinite strain axis for olivine. I was wondering if you had looked at how the ISA how well it predicted your more intense, more complicated.
I think the comparison. This is the. I mean, you don't, even if you compute the SKS splitting, okay, this is even more accurate than the ISA. You can see that there is no pattern. Okay, in this model where you just use one input velocity field. While if you use all different input velocity fields of your run, then you can reproduce something more similar to the observations.
Okay, so we have to proceed, otherwise we are too much running out of time.